K is positive or not. Up to now, we've always had K positive, so I'm going to put that here. So it's understood when I write these that K is positive. I want to talk about that too. But first things first. The first thing I wanted to do was to show you that the first case, the most special case, does not just apply to this. It applies to other things too. Let me give you a mixing problem. The typical mixing problem is, it gives another example. You've already done in recitation, and you did one for problem set, the problem of the two rooms filled with smoke. But let me do it just using letters so that you can, the ideas stand out a little more clearly, and you're not preoccupied with the numbers and calculating with the numbers and trying to get numerical examples. So it's the simplest case of mixing. It looks like this. You have a tank, a room, I don't know where everything's getting mixed in. It has a certain volume, which I'll call V. Something is flowing in, a gas or a liquid, and R will be the flow rate in some units. Now, since it can't pile up inside this sealed container, which I'm sure is full, the flow rate out must also be R. And what we're interested in is the amount of salt. So X, let's suppose these are fluid flows, and the dissolved substance that I'm talking about is not carbon monoxide. It's salt, is any dissolved substance, some pollutant or whatever the problem calls for. Let's use salt. So it's the amount of salt in the tank at time t. I'm interested in knowing how that varies with time. Now, there's nothing to be said about how it flows out. What flows out, of course, is what happens to be in the tank. But I do have to say what flows in. Now, the only convenient way to describe the inflow is in terms of its concentration. The salt will be dissolved in the inflowing water, and so there'll be a certain concentration. And as you'll see, for a secret reason, I'm going to give that the subscript E. So E is the concentration of the incoming salt. In other words, in the fluid, how many grams are there per liter in the incoming fluid? That's the data. So this is the data. The R is part of the data. R is the flow rate. V is the volume. I think I won't bother writing that down. And the problem is to determine what happens to X of t. Now, I strongly recommend you not attempt to work directly with the concentrations unless you feel you have a really good physical feeling for concentrations. I strongly recommend you work with the variable that you're given, namely the dependent variable is the amount of salt, grams. Well, because it's something you can physically think about. It's coming in, it's getting mixed up, and some of it's going out. So the basic equation is going to be that the rate of change of salt in the tank is the rate of salt inflow. Let me rate salt inflow minus the rate of salt outflow. Okay, at what rate is salt flowing in? Well, the flow rate is the flow rate of the liquid. I multiply the flow rate, 1 liter per minute, times the concentration, 3 grams per liter. That means 3 grams per minute. It's going to be, therefore, the product of the flow rate and the concentration, incoming concentration. How about the rate of the salt outflow? Well, again, the rate of the liquid outflow is R, and what is the concentration of salt as it comes in the outflow? I must use, when you talk flow rates, the other factor must be the concentration, not the amount. So what is the concentration in the outflow? Well, it's the amount of salt in the tank divided by its volume. So the analog of the concentration here is X divided by V. Now here's a typical messy equation. dx dt, let's write it in the standard linear form, plus R times X over V equals R times the given concentration, which is a function of time. Now, this is going to be some given function, and there will be no reason whatever why you can't solve it in that form, and that's normally what you will do. Nonetheless, in trying to understand how it fits into this paradigm, which kind of equation is it? Well, clearly there's an awkwardness in that on the right-hand side we have concentration, and on the left-hand side we seem to have amounts. Now, the way to understand the equation as opposed to the way to solve it, well, it's a step on the way to solving it. You can, but I emphasize, you can and normally will solve it in exactly that form. But to understand what's happening, it's better to express it in terms of concentration entirely, and that's why it's called the concentration or the diffusion, concentration, diffusion equation. So I'm going to convert this to concentrations. Now, there's no problem here. X over V is the concentration in the tank. And now, immediately you see, hey, it looks like it's going to come out just in the first form. But wait a minute. How about the X? How do I convert that? Well, what's the relation between X? So, if the concentration in the tank is equal to X over V, so the tank concentration, then X is equal to C times the constant V, and dx dt, therefore, will be V times dc dt. You see that? Now, that's not in standard form. Let's put it in standard form. To put it in standard form, I see now that it's not R that's the critical quantity. It's R divided by V. So it's dc dt, C prime, is E plus R divided by V. I'm going to call that K. Kc, no, let's not. R divided by V is equal to R divided by V times CE. That's the equation expressed in form of where the concentration is the dependent variable rather than the salt, amount of salt itself. And you can see it falls exactly in this category. That means that I can talk about it, the natural way to talk about this equation is in terms of the same way we talked about the temperature equation. I said concentration. I mean, it's that concentration has nothing to do with this concentration. This is the diffusion model where salt outside, salt solution outside, cell in the middle, salt diffusing through a semi-permeable membrane into that uses Newton's law of diffusion, except he didn't do a law of diffusion. But he's sticky. His name is attached to everything. So that's this concentration model. It's the one entirely analogous to the temperature, and the physical setup is the same. This one is entirely different. Mixing in this form of this problem has really nothing to do with this model whatsoever. But nor does that concentration have anything to do with this concentration, which refers to the result of the mixing in the tank. But what happens is the differential equation is the same. The language of input and response that we talked about in the old is also available here. So everything is the same. And the most interesting thing is that it shows that the analog of the conductivity, the K, the analog of conductivity and diffusivity is this quantity. I should not be considering R and V by themselves. I should be considering as the basic quantity the ratio of those two. Now, why is that? Is the basic parameter. What is this? Well, R is the rate of outflow and the rate of inflow. What's R over V? R over V is the fractional rate of outflow. In other words, if R over V is 1/10, it means that 1/10 of the tank will be emptied in a minute, say. In other words, we've lumped constants into these two constants into a single K, and at the same time have simplified the units. What are the units? This is volume per minute. This is volume, so it's simply reciprocal minutes. Reciprocal time, which was the same units that diffusivity and conductivity had. Reciprocal time. The space variables have entirely disappeared. So in that way, it's simplified conceptually, and now you can answer the same type of questions we asked before about this. I think it would be better for us to move on, though. Well, just example one, really simple thing. Suppose since we spent so much time worrying about what was happening with sinusoidal inputs, I mean, when could CE be sinusoidal, for example? Well, roughly sinusoidal if, for example, if some factory were polluting, this were a lake, then some factory were polluting it, but, in the beginning, at the beginning of the day, they produced a lot of the pollutant, and by the end of the day, when it wound down, it might well happen that the concentration of pollutant in the incoming stream would vary sinusoidally, with a 24-hour cycle. A 24-hour cycle. And then we would be asking, so suppose this varies sinusoidally, in other words, is like cosine omega t. I'm asking how closely does the concentration in the tank follow C sub E? Now, what would that depend upon? Think about it. Well, the answer, suppose K is large. Closely, let's just analyze one case. If K is big. Now, what would make K big? We know that from the temperature thing. If the conductivity is high, then the inner temperature will follow the outer temperature closely. And the same thing with the diffusion model. Well, we, of course, therefore, since the equation is the same, we must get the same result here. Now, what would make K big? If R is big, if the flow rate is very fast, we will expect the concentration of the inside of that tank to pretty match fairly closely the concentration of the pollutant, of the incoming salt solution. Or if the tank is very small. For fixed flow rate, if the tank is very small, well, then it gets emptied quickly. So both of these I think, are intuitive results. And of course, as before, we got them from that by trying to analyze the final form of the solution. In other words, we got them by looking at that form of the solution up there and seeing if K is big, if K increases, what happens to the amplitude and what happens to the phase lag. But that summarizes the two. So this means, closely means that the phase lag is big or small. The lag is small. And the amplitude is, well, the biggest the amplitude could ever be is 1, because that's the amplitude of this. So the amplitude is near 1. 1 because that's the amplitude of the incoming signal, input, whatever you want to call it. Okay, now I'd like to spend the rest of the time talking about the failures of number 1 and when you have to use number 2 and when even number 2 is no good. So let me end first order equations by putting my worst foot forward. Well, I'm just trying to avoid disappointment and misapprehensions for you. I don't want you to leave this room saying, well, he said that, and, you know. Okay. So the first one you're going to encounter very shortly where 1 is not satisfied but 2 is. So on some examples where you need 2. Well, it's going to happen right here. Somebody sooner or later is going to draw on that loathsome orange chalk, which is unerasable. Something which looks like that. Remember, you saw it here first. R. Yeah, we had that. Okay, see, you had it in high school too. That's a capacitance. This is a resistance. That's an electromotive force, a battery or a source of alternating current, something like that. Now, of course, what you're interested in is the current, how the current flows in the circuit. But since current across the capacitance doesn't make sense, you have to talk about the charge on the capacitance. So Q, it's customary in a circuit this simple to use as the variable not current, but the charge on the capacitance. And then Kirchhoff's, you're also supposed to know that the time derivative of Q is what's called the current in the circuit. That's sort of intuitive. But look, I in a physics class, J in an electrical engineering class, and Y, not the letter Y, but why is that? That is because electrical engineers use lots and lots of complex numbers, and therefore they have to call current J, I guess. I think they do J in physics too now. No, they don't. I don't know. So I is ambiguous if you're in that particular subject, and it's customary to use, I don't know. Now it's completely safe. Okay, where are we? Well, the law is, the basic differential equation is Kirchhoff's voltage law, that the sum of the voltage drops across these three has to be 0. And so it's R times I, which is dq dt. That's the Ohm's law. That's the voltage drop across the resistance. The voltage drop across the capacitance is Coulomb's law, one form of Coulomb's law. It's Q divided by C. And that has to be the voltage drop. And then there's some sign conventions. So this is either plus or minus, depending on your sign conventions, but it's E of t. Now, if I put that in standard form, I probably should say Q prime plus Q over RC equals, well, I suppose E over R. But this is what would appear in the equation, but it's not the natural thing. The K is 1 over RC, and that's the reciprocal. The RC constant is what everybody knows is important when you talk about a little circuit of that form. On the other hand, the right-hand side, it's quite unnatural to try to stick on the right-hand side that same RC. Call this EC over RC. People don't do that, and therefore it doesn't really fall into the paradigm of that first equation. It's the second equation that it really falls into. Another simple example of this is chain decay, radioactive chain decay. Where, let's say, the substance, radioactive substance A, decays into, let's say, one atom of this produces one atom of that for simplicity. So it decays into B, which then still is radioactive and decays further. Okay, what's the differential equation, which is going to be, it's going to cover this situation. What I want to know is how much B there is at any given time. So I want a differential equation for the quantity of the radioactive product at any given time. Well, what's it going to look like? Well, it's the amount coming in minus the amount going out, so to speak. The rate of inflow minus the rate of outflow, except it's not the same type of physical flow we had before. How fast is it coming in? Well, A is decaying at a certain rate, and so it's the rate at which A decays is by the basic radioactive law. It's K1, it's constant, decay constant, times the amount of A present. if I use the differential equation with A here, I'd have to put a negative sign because it's the rate at which that stuff is leaving A. But I'm interested in the rate at which it's coming into B. So it has a positive sign. And then the rate at which B is decaying, and therefore the quantity of B is, good B is gone, that will have some other constant, B. So that will be the equation. And to avoid having two dependent variables in there, we know how A is decaying. It's going to look like, so it's K1, some constant times A, A will be e to the negative, the decay law, so times the initial amount that was there, times e to the negative K1t. That's how much A there is at any given time. It's decaying by radioactive decay law, minus K2b. Okay, so how does the differential equation look like? It looks like B prime plus K2b equals an exponential, K1A0 e to the negative K1t, but there's no reason to expect that that constant really has anything to do with K2. It's unnatural to put it in that form. And so here, too, is another example where it's the second form, which is the correct one. Now, in the last 2 minutes, I wish to alienate half the class by pointing out that if K is less than 0, none of the terminology of transients, steady state, input, response applies. The technique of solving the equation is identical, but you cannot interpret. So the technique is the same, and therefore it's worth learning. The technique is the same. In other words, the solution will be still e to the negative kt integral q of t e to the kt dt plus a constant times e to the k. Oh, this is terrible. No. dy dt. Let's give an example. The equation I'm going to look at is something that looks like this. Y equals q of t, let's say. Okay? A constant, but the constant A is positive, so the constant here is negative. Then when I solve, my K, in other words, is now properly written as negative A, and therefore this formula should now become not this, but the negative A is, the negative K is AT. And here it's negative AT, and here it is positive AT. Now, why is it, if this is going to be the solution, why is it all those things totally irrelevant? This is not a transient any longer, because if A is positive, this goes to infinity. Or it might go to minus infinity if C is negative. So it's not transient, it's not going to 0, and it depends heavily on the initial condition. That means that of these two functions, this is the important guy. This is just fixed, some fixed function. Everything, in other words, is going to depend upon the initial conditions, whereas in the other cases we have been studying, the initial conditions after a while don't matter anymore. Now, why did I say I would alienate half of you? Well, because in what subjects will A be positive? In what subjects will K be negative? K is typically negative in biology, economics, Sloan. In other words, the simple thing is, think of it in biology. What's the biological equation? What's the simplest equation for population growth? Well, it is dp dt equals some, if the population is growing, A times P, and A is a positive number. That means P prime minus AP is 0. So the thing I want to leave you with is this. If life is involved, K is likely to be negative. K is positive when inanimate things are involved. I won't say dead, inanimate.